down on the ground quickly, so they do not create any harmful effects. Okay, but the problem is with the smaller size particles. Then we moved on and discussed about the definition for particulate matter. Why this definition is important is based on how you measure, what instrument you use to measure the particulate matter, the composition of the particulate matter is going to be different. So we need to standardize this process of measuring this particulate matter. Otherwise, based on the method you adopt or the equipment you use, the composition of the particulate matter is going to be different. That's why considering this US Environmental Protection Agency has defined this particulate matter, PM, and also they have given conditions for measuring this particulate matter in a typical equipment called dilution tunnel. So this is a standard equipment accepted worldwide to measure the particulate matter. I think this is used to measure the mass, PM mass. So we regulate in the emission mandates, we regulate the particulate matter mass. So we need to measure this PM mass, okay? And the important point here is PM mass do not distinguish between the different size particles, smaller or larger. Okay, it's only the total mass. So it is not categorizing the size of the particles, it's only mass. Okay, so according to this definition, we are getting particulate matter by allowing diluted exhaust gas to flow through this dilution tunnel. So this dilution tunnel is a steel tube of 30 centimeter diameter, 1 feet. Okay, stainless steel tube of 30 centimeter diameter, and inside that you have this filter. This filter material is given. It is Teflon coated with fiberglass. So we know that the exhaust gas exists at different temperatures in the engine tailpipe based on the engine operating condition. So based on the speed and load at which the engine is run, the temperature of the exhaust gas as well as the composition of the exhaust gas is going to be different, right? Considering this, we are creating a controlled condition. We are measuring this at 52 degrees Celsius or below the temperature. Okay, that is a defined temperature that measurement is being carried out. 52 or below 52 is a measurement temperature. Now, to get this 52 or below 52, you have to mix exhaust gas with the air. So that's what we are doing here. It's a diluted exhaust gas. What is the proportion of air in exhaust gas? It's going to be different. It varies anywhere between 3:1 to 20:1, right? The first one is air and second one is exhaust gas. So you may have to add more air if the exhaust temperature is high. Otherwise, you cannot bring to this level, 52 degrees Celsius. Okay, so they have defined this PM as any substance that is collected in this filter other than water, H2O, because we are burning hydrocarbon fuel. H2O is one of the product. Other than H2O, anything else that is collected in this filter is what is defined as a particulate matter. And to measure this, we have a control condition. We are allowing diluted exhaust gas at 52 degrees or below that to pass through this filter. And we measure the mass of the filter before we allow the diluted exhaust to flow through, and after the diluted exhaust gas that pass through. Okay, so the difference between the mass of the filter, clean filter, and after filtering, right? After you allow the exhaust gas, the particles will get settled down on the filter, that is trapped. Okay, so the mass is going to be different for the clean filter and after you allow the diluted exhaust gas to flow through the filter. This difference in mass is a measure of particulate matter. Okay, it's a PM mass. So that is how we measure it. Then you need to do a detailed characterization to get. So what you get out of whatever we discussed so far is only the mass, total PM mass, right? So we need to do detailed characterization using analytical technique to find out what is the composition of the particulate matter. So based on the analytical techniques, I already told you that even today we have not characterized this particulate matter very well. Meaning, it is some of the constituents are unknown in PM. Even today, we don't know the exact composition of particulate matter. But based on whatever techniques we have, these three components are identified as the constituents of particulate matter or composition of particulate matter. So it consists of soot. Soot is solid carbon. It's around 40%. This number is going to be different based on the type of engine. For example, if it is a heavy engine, heavy duty engine, okay, heavier engine with a larger rated power, the concentration will be soot value will be different. In a small diesel engine like off-road small diesel engine, the value of soot will be different. So based on the type of engine in terms of rated power, and also based on the operating conditions, the number is going to be different. I have given only some typical concentration to get the feel of what will be the value of the individual constituents present in the particulate matter. So there are three components. One is soot. Second one is SOF. SOF is soluble organic fraction. And the third one is inorganic derivatives. Inorganic derivative, okay. Typical split of these three are 40%. Then you have 30% of soluble organic fraction, 30% of inorganic derivative. 40, 30, 30, and this number will vary. For example, the soluble organic fraction, the source for soluble organic fraction is unburned fuel or partially burned fuel as well as lubricating oil. Partially burned fuel or lubricating oil is what is a liquid particle carried away in the gas stream. That is what is this soluble organic fraction. Please remember the first definition we had. PM is nothing but it's a particle, solid particle or liquid particle suspended in gas stream. Solid particles are soot, liquid particles are unburnt or partially burnt fuel and lubricating oil. And in the gas stream, you have several oxides of nitrogen and sulfur as indicated here, as well as sulfate. So these are the gas phase species, okay, we have in the PM. Nitrogen dioxide, sulfur dioxide is also being carried out in the gas stream. So you have a soot, and the soot carries liquid particles, okay, soluble organic fraction, and the soot solid matter as well as this liquid material all are suspended in the gas stream. In the gas stream, you have these oxides of nitrogen and sulfur, which are designated as inorganic. Anything other than carbon is inorganic. Okay, so that's why it is called inorganic derivative. So you have these three components present in particulate matter. Okay, that is a typical composition. The soluble organic fraction is generally very high at low load condition, where the unburned or partially burned fuel and lube oil concentration in the exhaust is high. So at high load, this will go down. This 30% will go down to up to say 5% or so, because at high load, this will be oxidized very well. Fuel and lube oil will be oxidized very well. So you will have very limited liquid particles present in the exhaust gas stream. So this number will go down at high load, but at low load, you will have a high proportion of soluble organic fraction. Okay, at high load, you will have a high concentration of soot, because the solid carbon concentration, you can expect it to be high at high load since you are burning more fuel. Okay. So out of these three constituent or composition, just now we have discussed, the major component is soot. So if you have to control particulate emissions from diesel engine, you need to control soot. Why? Because the soot or solid carbon is what is giving surface for the other particles to get inside. Okay, for example, if you don't have soot, you don't have the soluble organic fraction, because soot is carrying the soluble organic fraction. So soluble organic fraction or any liquid phase particle are carried away by this soot. Okay, so since soot has a surface, this liquid particle go and settle down on the surface, and that is how it is being carried out in the exhaust. So if you have to control the particulate matter, the primary control mechanism that you need to devise is to target the soot. You should avoid forming soot. If you eliminate soot, you can eliminate SOF and inorganic derivatives. Of course, this is a gas stream. It will appear as oxides of nitrogen. You will see here that you also have this NO2 considered in the PM, one of the component in the PM. Okay. So the mechanism that we devise to control PM should be targeting the soot. That's why it's very important to understand the mechanism behind the soot formation. So that's what we are doing here. We are trying to understand the mechanism behind the soot formation. It happens in 3 steps as indicated here. The first step is pyrolysis reaction. Then you have surface growth reaction, then coagulation. These three are the processes involved in getting the soot particles in the engine exhaust. So what is this pyrolysis? Any idea?
Breaking up of hydrocarbon chains.
Breaking up of hydrocarbon chains. Under what conditions?
Thermal cracking, sir.
So it is
In the sense by high temperature and pressure. And
high temperature and pressure. So you are missing one of the important term here. When you talk about cracking at high pressure and temperature, something is missing, which makes the
Time
process.
in the presence of catalyst.
No. This is thermal cracking. Without so catalytic cracking is in presence of catalyst. Thermal cracking can happen without catalyst. In fact, inside the engine combustion chamber, you are not adding any catalyst there. It's only fuel that undergoes cracking at high temperature, which is what is thermal cracking.
Any factor related to time, sir, like in a very short duration.
No, always it is short duration in engine combustion. Already we discussed about that. All these reactions will take place in nanosecond time scale or at the most microsecond time scale.
In the absence of oxygen?
Yes, in the absence of oxygen, or we can say that very limited oxygen. That is how pyrolysis reaction will take place. So it happens in oxygen deficient environment. In the absence of oxygen, our O2 concentration will be very, very low. Okay, so it will be considerably low. So inside the engine, if you have rich region, fuel rich region, you can say that in those regions, the oxygen content is very limited. So the source for forming soot is oxygen deficiency. I already said about that. You could see the Phi range, which we have already discussed. It's 2 to 4. So ideal Phi range for forming soot, 2 to 4. So it's a fuel-rich environment. In other words, it's an oxygen-deficient environment. That is what is causing this pyrolysis at high temperature. So for this reaction to happen, there are two conditions. One, high temperature. Second one, oxygen deficiency. If oxygen is present, what will happen at high temperature?
It will dissociate and form oxygen radical.
So it will oxidize, right? You won't have cracking, rather than you will have oxidation reaction. Do you understand what I'm saying?
Right, sir.
At high temperature, if you have oxygen, enough oxygen, then the hydrocarbon will oxidize. It won't crack. Okay, so the important condition here is you have high temperature and you have oxygen deficiency. The combination of high temperature and oxygen deficiency is what is causing this cracking. So when I say cracking, what I mean heavier hydrocarbon, which we discussed in chapter 1, breakdown and form a smaller chain molecule. For example, if you consider normal paraffin, you have a lengthy chain, right? When I say cracking, this lengthy chain will be broken down into shorter chain. So heavier chain will get down to shorter chain because of this cracking. This is what I mean by cracking process. So several small hydrocarbon intermediate species will form during cracking from a heavier molecule to a lighter or shorter molecule. That is what is forming during thermal cracking. And finally, what it will lead to forming something called acetylene or PAH, which is polyaromatic hydrocarbon. Okay, heavy hydrocarbon present in diesel, because this diesel is what is diesel combustion is what is causing this soot. So this heavy hydrocarbon present in diesel breakdown due to thermal cracking leads to forming several short chain hydrocarbon. Finally, it will lead to forming acetylene or PAH. And this acetylene or PAH are called soot precursors. So you are forming something called a soot precursor. Precursor is something that leads to forming soot. So heavier molecule breakdown to shorter molecule, and finally it leads to forming this gas-phase species, acetylene and PAH, which are called soot precursor. Why this acetylene or PAH, especially PAH, we are interested in, and why we are calling this a soot precursor is it consists of very high carbon proportion, very less hydrogen proportion. Okay, soot is solid carbon, right? So that's why this species are called soot precursors. So finally, it leads to forming soot with a typical molecular formula of C8H, C9H. This is a typical formula. Okay, so you have this gas phase species acetylene or PAH. Once upon condensation, it leads to forming something called soot nuclei. Use the word soot nuclei. So gas phase species condense and form this solid phase species, which is soot nuclei with a typical formula of C8, C9, C10H. So there is a negligible hydrocarbon. There is a high proportion of carbon. That is what is soot. So it all starts with this thermal cracking, which is a pyrolysis reaction under oxygen deficient environment with the P2 to 4 range or a wide range of pressure and temperature. As you could see here, this reaction can happen at any anywhere between 1000 to 2800 Kelvin temperature range. Okay, anyway, it's starting at 1000, it's relatively a higher temperature. It can go all the way up to 2800 Kelvin. So high temperature, you will have a high rate of pyrolysis reaction. Pressure is also over a wide range, 50 to 100 bar. These conditions are very well reached in IC engine combustion, diesel combustion. That's why, and also you have local rich region, local region. You will have very well this 2 to 4 equivalence ratio region. So this combination of pressure, temperature, and equivalence ratio is leading to forming soot. Once soot form, that is how the soot form in a typical pyrolysis process, okay, because of cracking. Once it form, it leads to the second process called growth, surface growth. The surface of the soot is going to grow.